All right, so welcome back to our second online lab. We hope all of you are adjusting well to the online version of all of your classes and keeping up with your work. Just want to give an update as to how myself and Professor Collins are doing. We continue to get together a few times a week, of course, while staying 6 feet apart from one another to let our dogs play together, Beaker and Dory, pictured here. Of course, while Professor Collins consumes massive quantities of Pepsi, his favorite beverage. So that's a quick update as to what we are up to. And of course, this week we want to continue your musical education. And so we posted the Spotify playlist on the course Moodle page for the greatest hits of Elton John. And so we fully expect you to listen to at least a few of those songs on the playlist over this next week. All right, so this week's lab revolves around column chromatography, and it ties in very nicely to what we did last week with the TLC lab. Very, very similar concepts. So an overview of column chromatography, it's a technique used to separate mixtures, again, just like TLC, except in this case, you can actually isolate those mixtures. So you remember when you run a TLC plate, all you're doing is separating compounds in a mixture, but you're not actually collecting them and then doing anything with those compounds. You're just trying to separate them. With column chromatography, you're separating them, but then you're actually collecting each individual compound. So let's say that you had 3 compounds to start with in a single vial. By the end of column chromatography, you'd be able to have one vial of one compound, another vial of another compound, and then a third vial of the third compound. So it's a great way to actually collect and separate your compounds from a mixture. And we perform column chromatography in a glass column of silica gel. So it's the same exact stationary phase as what's on a TLC plate. It's just in a glass column. And so what you do, instead of spotting your mixture on the baseline, just like you would do in TLC, you pipette or load your mixture on top of the silica gel that's contained in the column. And then what you do is you add a bunch of solvent. This can be one or a combination of solvents. Again, your mobile phase. And thanks to gravity, that mobile phase carries each compound down the column. So in TLC, the mobile phase carries each compound up the TLC plate. In column chromatography, the mobile phase carries each compound down the column. And eventually, the mobile phase that contains each compound comes off of the column, and you collect those in either test tubes or beakers or vials or whatever, and we call those fractions. And then once your column is finished, once you actually separate your mixtures and you collected each of them, you just analyze them by TLC. So a lot of nice tie-ins compared to what we were doing last week. So the first thing that you have to do before you actually run your column is figure out what your mobile phase is going to be, or mobile phase is. So what you do is you run multiple TLC plates, just like we did last week, and we just change the solvent each time. So we have a few examples here. We have 4 different TLC plates in which we use 4 different solvents to try to separate an orange dye and a blue dye, of course, for Bucknell colors. So if we look at the first TLC plate, we notice that the blue dye and the orange dye didn't separate a whole lot, and they also ran really far up the TLC plate. And so if you were to actually run a column using solvent number 1, what would most likely happen is both the orange dye and the blue dye would actually end up in your first or second, basically in the same fraction, and thus defeats the point of actually separating them. So we would say that solvent 1 is a bad solvent. We wouldn't want to pick that mobile phase to run our column in. Now jumping over to solvent number 2, look at this great separation. The blue dye hardly moves from the baseline, whereas the orange dye travels almost all the way up the TLC plate. And so this is a great solvent because you will get total separation. You would actually be able to isolate this orange dye in your first or second fraction, say, and the blue dye would hardly even travel down the column. So this would be a great solvent to actually separate the orange dye from the blue dye. And then pretty similar for solvent 3, except now it looks like the blue dye traveled all the way up the TLC plate and the orange dye hardly moved. So it looks like if we want to actually collect the orange dye, we should start running our column with solvent number 2. And at some point, we'll collect the orange dye, and the blue dye will still be on the column. Now, we actually want to isolate this blue dye, so we would then switch to solvent number 3. This orange dye wouldn't exist because it had already traveled off the column. And so once we switch to solvent number 3, the blue dye would actually start moving down the column, and finally, we'd be able to separate it in a different fraction. Finally, I just want to point out, solvent 4 would technically work. You do get separation here between the orange dye and the blue dye, and you could really move slowly enough to actually separate them into different fractions. The challenge is this would take a lot of solvent and a lot of time. Imagine it took this much solvent from the baseline to the top of the TLC plate, took that much solvent just to barely move the blue dye and the orange dye. So you can imagine how much solvent would actually be needed in the column to actually get each of these dyes to come off. So ideally, again, when you're looking at mobile phases for your column, you do want separation, but you also want to pick solvents that are actually going to move each compound off the column, somewhat quickly. Otherwise, you're gonna have to keep adding, essentially liters of solvent to get each of those off the column. Okay, so how do we actually set up our column? It's pretty similar to a burette, and in this case, we actually use the burette. But a column is just a long glass tube with a stopcock at the bottom, and we fill it with silica gel, typically as our stationary phase. The challenge is if you didn't put anything at the bottom here and you opened up the burette, all the silica gel would just immediately run onto the bench top. So what we do is we take a piece of glass wool, which actually won't interact with any of the compounds, and we add the glass wool to the bottom of the burette, and then we put the silica gel on top so that it doesn't, run out onto the bench top. And there's a lot more advanced theory as to how much silica gel you need for a column, but we're not going to cover that in the lab experiment today. So once you have your silica gel in the column, you would add your unknown mixture that you want to separate. Now, another thing that a lot of organic chemists will do very commonly is actually first dissolve the silica gel in their mobile phase and then add it to the column so that the column essentially has mobile phase already running through it. But for today's lab, we actually don't need to do that just because of the separation we get with our compounds. Okay, so what does running a column actually look like? So we have our column here that's filled with our stationary phase, which in this case would be silica gel. And then you would essentially take a glass pipette and dispense your sample at the very top of it. So let's say that we have this mixture of 2 dyes, it looks purple, and upon adding your first mobile phase, your first solvent, we see that that band starts to separate into 2 different bands, a blue one and a red one. So we see that we're already getting separation here. Now, as we continue to add solvent, it's going to start coming out of the column, and we collect those, again, in a test tube or a vial. We call each of these fractions. But as we continue to add more and more of our first solvents, we see that we're now getting separation, just like you would see with a TLC plate. Notice that the red compound is traveling very quickly down the column, whereas the blue compound is slowly traveling down the column. And again, that goes back to the interactions of each compound with the stationary phase. This blue dye or compound has strong interactions with the stationary phase, so it's going to travel very slowly down the column, whereas this red compound has very weak interactions with the stationary phase, it's going to travel very quickly down the column. So we can generally say that the red compound is a lot more nonpolar, whereas the blue compound is a lot more polar. And that's why we see the blue compound travels down the column much slower. So anyway, you continue to add more and more of your solvent, and eventually your red compound starts coming out of the burette or the column. We collect it into, again, a test tube or a vial. And then at that point, you would switch your mobile phase solvent so that you can much more quickly get the second compound, the blue compound, off the column. But between this step and this step, you would actually switch to a different test tube so that the blue compound doesn't end up in the test tube containing the red compound. You use again two or more different test tubes or vials. All right, and then once your column is finished, you want to analyze the results. Again, looks like we have 6 different containers down here. We call each of these fractions again. And what you would do is take a TLC of this fraction. So you would use your capillary tube, withdraw some liquid from this fraction, spot it on the baseline of a TLC plate, and run that. And you do the same thing for this one and this one and all the rest of them. And that just essentially verifies that there's no red dye in this fraction and no red dye in this fraction. All of it is contained in this fraction. Because you can imagine if you want to eventually isolate this red dye, by putting it on a rotovap to remove all the solvent, if for whatever reason there was some red dye in here, you wouldn't want to just throw this out. You would actually want to combine these 2 fractions so that you maximize the amount of compound that you actually isolated. Alternatively, if you ended up with really poor separation and you had a mixture of red dye and blue dye in this fraction here, you wouldn't actually want to isolate that because you didn't separate the 2 compounds. So one option is you could run another column on just this fraction and hopefully do a better job so that you would actually separate the red dye and the blue dye. But based on these results, at least just visually, it looks like we were able to separate the red dye from the blue dye. But it's always good to do TLC just to verify that. All right, so that's one way of actually separating a mixture of 2 compounds. Another way is essentially the same exact technique, except instead of silica gel, you use a special kind of silica gel. And this silica gel contains these very long carbon chains, very long alkyl groups. So the stationary phase, instead of containing OH groups, contain these alkyl groups, and the stationary phase is very nonpolar then. And so if your stationary phase is nonpolar, it's going to strongly interact with very nonpolar compounds, like our naphthalene here, which contains only carbon and hydrogen atoms. So the order in which the compounds travel down the column is actually reversed. And that's why we call this reverse phase column chromatography. Because instead of nonpolar compounds traveling down very quickly, nonpolar compounds move very slowly down the column, and then polar compounds move very quickly because polar compounds don't really interact with these alkyl groups relative to these nonpolar compounds. So you will see after watching the video how this process works. It's really the same thing. You load your sample the same way at the top of your column. It's just the compounds come off in a different order. And you would still TLC each of the fractions, and we did this for you. We posted data on that, and it's up to you to analyze those results. Okay, so the goal for today's lab, we have a red dye and a blue dye that we actually combined into one vial and ran a normal phase column and a reverse phase column on that mixture. And it's up to you to verify that those 2 compounds actually were separated based on the 2 methods. But before you actually do that, it's up to you to figure out what 2 solvents would be needed to get the job done. So that's what all the different parts are. First, you analyze the TLC, first TLCs, so that you can figure out which solvents you should use. Then you analyze the TLC results from the normal phase column, and then the results of the reverse phase column. So on Moodle, what you should do is watch the YouTube videos, the playlist, along with the this lecture, right? And we are checking Moodle to make sure that you do that. And so we'll give you 10 points just for doing that. And then walk through the handout, analyze the data, and go back and forth between the handout and the videos so that you can complete the column handout data quiz along with the column post-lab quiz. And that's everything for this week's experiment.